All right. Hopefully this works now. I just discovered the built-in Windows screen recorder, which apparently is designed for recording video games, but seems to also work in Excel. So good evening, afternoon, morning, everybody, whatever it is, wherever you are. I am making this video to correct a mistake I made during lab yesterday, a mistake that we figured out in the section immediately following you guys, regarding the fitting of our data to a mathematical model. Remember, there was some question as to what was going on there. I wrote up on the board the actual model for the relationship between a pendulum's period and its length, and we couldn't figure out how to, it was a square root function, and we could not figure out how to find a square root function, how to fit data to a square root function in Excel. Well, luckily we figured it out in the following section, so I'm going to share that with you guys. Using the data, I don't want to do that. I'm using the data from the Lab 2 PowerPoint, the example data, which I'm copying and pasting into this Excel notebook, like so. Stretch that out so you can see it. Let's grab this stuff here. I'm also using the latest version of Excel, version 2016, which I think is newer than what they have on the computers in the lab, unfortunately, because I discovered there's a really convenient tool here. If you want to make a chart, just highlight your data, click Insert, Recommended Charts, and boom, the line chart is the first one, or I guess they call it a scatter chart. So there, we've got our chart. I'm going to make it a little bit bigger so it's easier to see. And the default here is they are connecting all of the data points with straight lines. We actually don't want that because it kind of makes it hard to see whether or not our trend line is fitting. So, let's see, I'm going to right click on that blue line, click Format Data Series, and we get this side panel that opens up. If you click the Fill and Line paint bucket thing and select no line, then that all disappears. So we're also going to add some error bars, which can be done by clicking the plus sign, going to error bars, clicking the little arrow for more options, and click error bar options here. We want the fixed value to be 1/10 of a second, according to this PowerPoint that I'm grabbing this data from. So pressing enter, boom, there are our error bars properly set at 1/10 of a second. Why is this at 250 now? Can I change that? No, just behave stupidly. Actually, if I click the numbers, click axis options, set that to 200. There. Okay, so then we are going to fit a trend line. Actually, I'm going to make this chart a little prettier by giving it a proper title. Pendulum period versus length. And I'll even add some axes labels, axes titles. Axis title, this one is the pendulum length on the horizontal axis, and come on, select it. There we go, the pendulum period on the vertical axis. Okay, now we're going to add a trend line by hitting the plus sign, go down to trend line, click this little arrow, or that's legend. Trend line is down here. For more options, the default option is a linear fit, which is why this dashed line has appeared here, and it's pretty good, but not great. These data points are all above the line, these points are below the line, but we can get a better understanding of the goodness of our fit, so to speak, by checking the two boxes at the bottom of this panel, display equation on chart and display R-squared value on chart. Both of those have appeared here. They are really small and difficult to read. You can fix that by selecting all of that stuff, and it appeared just a minute ago and then it disappeared. Well, make the text bigger. So I'm going to do that by going to Home and clicking that button a bunch of times. That should do. Move this box down here. I said down here. Very good. Okay, so this expression here is the equation of this line. This number is the slope. This is our y-intercept. And on the second row, this r-squared value is a measure of how good of a fit this line is for our data. Basically, ideally, this r-squared value should be 1 exactly. And the closer it is to 1, the better. And right now it's 0.96 something, so that's pretty close. That would be a reasonably good fit. However, we have more options to play with. We can do better. If we go back to not label, we want to click on the trend line again. There we go, format trend line. We have other functions to try fitting to, such as an exponential function. So here you can see how our dashed line is no longer a straight line. It's now a curve that is curving upwards, which you wouldn't expect that to be a better fit because our data points seem to be curving downwards. However, nothing here has changed, and I think that is a bug in Excel, because if you click the trend line again and you get this panel and uncheck these two bottom boxes, that all disappears, recheck them, and now a new function, an exponential function, has appeared with a new r-squared value that is, well, farther away from 1. It was 0.96, now it's 0.8486 something. That happens when you change the text size, because from now on, as long as we don't change the text size, if we go back to linear, we get a linear equation and a better r-squared. Going back to exponential, you get an exponential equation and a less gooder r-squared. Let's try a logarithmic fit. Not bad. We have a logarithmic function. However, the r-squared is actually less than it was for a linear fit. Right now it's 9366. Before it was 964. So this linear fit is actually better than the logarithmic fit, even though the logarithmic fit is able to capture the curve in that data. In class, a lot of groups found luck with a polynomial fit. Like, look at that r-squared, 0.9966. And that curve sits right on all those data points, passes through all the error bars. That is a really good fit. If you increase the order of this polynomial, adding a cubic term, the fit gets even better. And if you can add a quartic or fourth power term, and it's even better. And by the time we add a quintic or fifth power term, our r-squared is 1. And the trend line passes directly through all of the data points. And we can go up to 6th order magnitude, but there's not really any difference there. The thing is, that's always the case with polynomial fits. By adding higher order terms, you can basically make your trend line squiggle enough so that it passes through all of your data points. And that's not useful to us right now. We're trying to find a simple expression, not something with a really small 5th power term, a really small 4th power, and really small 3rd power, and even a pretty small 2nd power term. So be careful when applying too many orders to your polynomial fits, because you'll always find a fit for sufficiently large orders, assuming that your data is smooth and well behaved. But we also have this option. the power fit. Ooh, look at that. So our second order polynomial had an r-squared value of 0.9966. The power fit, which also passes through all of the error bars, has a slightly better r-squared value of 0.998. This moving average thing, by the way, that's something totally different. You can ignore that one. But ignoring a crazy high order polynomial, this power fit is the best of the options we have available, and therefore this is the model for the relationship between a pendulum's length. Remember, the x in this case represents the pendulum's length, the y represents the pendulum's period. This is the best mathematical relationship that we can find by fitting our data. That's not a crazy high order polynomial. So what is this saying exactly? What does this model say? I can show you that, but in order to do that, I have to pause this recording and restart it in another window. So hold on to your seats. I'm going to try copying this. Okay, see you in the next video.